Hello, I'm Francesco De Luca, researcher at Tallinn University of Technology, together with Thomas Wortmann, lecturer at Xi'an Jiao Tong Liverpool University. We present the work multi-objective optimization for daylight retrofit. The objectives of the study are analyze the daylight potential of the retrofit of TATEC assembly hall through installation of windows and skylights, investigate trade-off solutions through multi-objective optimization for maximizing daylight and minimizing energy consumption, compare the performance of different multi-objective optimization algorithms, including RBFM-opt, a novel model-based algorithm. The novelty of the work resides in the lack of daylight and energy assessment of single-floor public buildings in Estonia, and in the scarcity of benchmark results for model-based multi-objective optimization algorithms combined with simulations. The building used for the research is the TATEC Assembly Hall, a Soviet-era windowless old building. A window on the south facade and multiple skylights have been considered as daylight sources. A parametric model is realized that automatically generates combinations of windows, skylights, and shading types and modifies their dimensions. Consequently, the parametric model integrates daylight and energy simulations and multi-objective optimization. The metric used for annual daylight availability is the continuous daylight autonomy with illuminance threshold 300 lux simulated on the reference plane. For energy simulations, thermal properties of walls and roof is that of the existing building elements. The electric lighting schedule is obtained from daylight simulations. For both simulations, the occupancy schedule is realized using existing building usage data. Energy simulations are performed to assess electric lighting, heating, and cooling energy consumption for the entire year for each daylight sources variation.
Daylight and energy models result in an optimization problem with 4 integer variables, 4 continuous variables, and 2 objectives. For the optimization benchmark, we compare 7 multi-objective algorithms using 5 runs of 500 function evaluations each. Every function evaluation requires an energy and a daylight simulation. 3 of the tested algorithms, HYPE, NSGA2, and MOIA-D, are evolutionary. These algorithms differ in terms of the metrics they use for the multi-objective optimization, with HYPE using the hypervolume metric. MHEACO is based on ant colony optimization and NSPSO on particle swarm optimization. RBF-MOPT is a model-based multi-objective algorithm developed by the second author and based on the single objective RBF-OPT. RBF-MOPT uses radial basis functions to learn and predict the objective, in this case a weighted sum of objectives. RBF-MOPT approximates a Pareto front by cycling over a sequence of weighted sums, as you can see on the right. Results from previous steps in the sequence are used in learning the new objective sum. This reuse of results to train the model potentially makes RBF-MOPT more efficient than the other population-based algorithms. Our results reveal that, perhaps intuitively, there is indeed a trade-off between energy consumption and daylight quality. According to the best-known front, the dotted line, energy consumption stays roughly constant until a continuous daylight autonomy of 45% and then rises, with a sharp increase starting at about 57%. This picture is represented accurately by the Pareto fronts found by RBF-OPT and HYPE, and less accurately by the other algorithms. In other words, the quality of the insights derived from multi-objective optimization depends on the algorithm. Our results show that only HYPE and RBF-MOPT perform well on this problem. RBF-MOPT 3 and 6 represent different algorithmic settings, but result in very similar outcomes. HYPE and RBF-MOPT result in Pareto curves that have a higher quality, as represented by the chart on the left, and that are more consistent, as represented by the chart on the right. Remarkably, the popular NSGA2 algorithm is the least robust.
Daylight and energy performance is analyzed for 170 trade-off solutions, those on the best-known Pareto front. Results show that the vast majority of the solutions include both daylight sources, the window and the skylights, with and without shading. Increasing natural light sources sites increases daylight potential at the expense of a higher energy consumption, though only for a limited number of cases. Of 170 trade-off solutions, 165 have a high daylight potential yielding an average continuous daylight autonomy above 50%, and of these 116 consume less energy than the base case of the existing building. For example, the minimum and average continuous daylight autonomy obtained using building configurations with window and skylights both without shading, and with window and skylights the latter with shading, is between 50.3% and 58.4%, and for these cases the total energy consumption is lower than the base case. It is worth noting that the external shading can reduce total energy consumption without decreasing significantly daylight availability. For example, shading for skylights can reduce up to 21% of total energy consumption at the expense of only 1% of daylight reduction. In conclusion, the research outcomes are: in northern climates, there is significant potential of appropriate daylight provision for single-hull public buildings without additional energy costs. Larger increases in daylight performance can result in larger energy costs due to cooling loads that are not offset by corresponding savings in electric lighting. For sufficient daylight, windows must be larger and skylights can be smaller. External shading reduces total energy consumption while maintaining sufficient daylight. Only Hype E and RBFM Opt can be recommended for multi-objective optimization problems with daylight and/or energy simulations. NSGA2 is the least robust algorithm for this problem. Thank you for the attention.